Let's close out this small little chapter with the ideas on dispersive and non-dispersive waves. I think you already know most of this. Non-dispersive waves, obviously the phase speed is just omega over k, and group velocity is d omega over dk. But if we assume omega is related to the spatial scales, frequency and spatial scales are related by this way, then the group velocity then just is the phase speed. Energy is not dispersed. The waveform retains the energy, and the group and the phase speed are the same. So the individual waves and the group move together, as we saw in this example in figure 4.1. So this is just a single sinusoidal wave. You can clearly see t plus delta t plus 2 delta t. The wave is quietly moving on, and in this case you have two waves nearby, so k plus delta k and omega plus delta omega. So there is a modulation and a group is formed, but you can see that the phase speed and the group velocity, they are not the same, but they are not dispersing energy. This is essentially a non-dispersive wave. It's maintaining its speed in both the group and the phase, and unlike the example of a stone thrown into a pond where waves radiate out and dissipate, which is a dispersive set of energies, in the real world we get Kelvin waves or gravity waves which are non-dispersive, and in that case the group velocity and the phase speed or phase velocity are not dependent on spatial scales, so they are non-dispersive. Background state doesn't matter in that case. Almost all waves in the ocean and atmosphere are dispersive, which means the frequency is a complex function of spatial scale. So something like omega is a function of k to the n, where k is the wave number, and of course group velocity is not equal to phase velocity, which combined with the background state has implications for not only modulation of the waveform, but also for aggregating wave energy in one place or dispersing it in another place. So look at this plot of the standing wave we had produced by two similar waves moving in opposite direction, and you can see here, even though you produce the standing wave, the waveform itself is dispersive. So the group velocity and the phase velocity are not the same in this case when you look at the individual waves and the speed of the group of waves. So that's just one example. We'll see many more examples as we go forward. In the case of non-dispersive waves, of course the group and the phase have the same speed, so if they are close to each other we can write them as the omega or k as omega plus delta omega divided by k plus delta k, and similarly omega minus delta omega or k minus delta k. So it's a group of waves, but it's non-dispersive, so the wave number, phase speed and group velocity are related. So we can move these and write it this way, and using the rule of the ratios they can be written as omega or delta omega equals k or delta k, or omega or k equals delta omega or delta k, which is basically phase speed equal to group phase velocity equal to group velocity. Somehow I keep saying phase speed and group velocity, but you know what I mean, right? Both are vectors unless they are just one directional unidirectional waves. Okay, so the transformation speed of the modulated amplitude is equal to that of an individual wave when you have non-dispersive waves. In the case of dispersive waves, then especially in the real ocean and atmosphere, the background state is going to be very important, which means, as I said already, the wave mode changes, frequency and wave numbers change, and we will have cases where meridional, zonal, and vertical wave numbers will be involved, and they are dispersive. So the interactions with the background state means energy can be aggregated in some places and not so in other places. So it turns out that for the tropical dynamics, waves are important, but the wave flow interactions are also very important. So we'll see examples. This is just a short chapter. I hope you understood the basic points of why we are looking at wave kinematics in terms of wave interactions and wave mean flow interactions, especially because longitudinally and latitudinally there are big variations in space in the background state. So waves are going to have lots of interactions with the background state.